So we're now finally ready to introduce tensors, and we'll do so as generalizations of what we've seen for vectors. So we saw that if we transform from one coordinate system, x1 to xn, to a barred coordinate system, x1 bar to xn bar, then under this transformation, our contravariant components of a vector, ti, satisfy this transformation law. And our covariant components satisfy this transformation law. So the tj and ti bar are a set of n functions, and they are contravariant components of a vector if they satisfy this law. So now we can think about tensors. And so let's think about the set of quantities t, and instead of just one index, let's have more than one index. So I1, let's have two of them, and actually let's have p contravariant indices. Let's have not 0 but 1 covariant index. Let's have 2. Maybe let's have q of them. Okay. And each of these indices runs from 1 to n. So this is a set of n to the power of p plus q components. And this set of quantities is called the component of a tensor if they transform in the following way. If in the barred coordinate system, t bar, we can write t bar I1, I2 up to IP and J1, J2 up to JQ, JQ, if we can write that this equals, and now for each covariant component we get one of these Jacobian matrix elements. So for the I1th term we have a dx bar I1 by a dx, and let's call it alpha 1. And here we have t unbarred, alpha 1, alpha 2, up to alpha p. And let's call it beta 1, beta 2, up to beta 3, beta q, sorry. So each of our contravariant components gets one of these Jacobian matrix elements. So we have a dx bar IP by a dx alpha p. Okay, so there's multiplications involved here. And each of our covariant components gets one of these guys. So it's dx beta 1 by dx bar j1 up to dx beta n by dx bar jn. Okay, so this defines what the components of a tensor are. And the quantity p plus q is called the rank of a tensor. Okay, and you have a rank of a tensor, and it's got a type, and the type is called pq. So as an example, our contravariant components have one single index. So let's think about Ti. This has P equals 1. It has Q equals 0. There are no covariant components. So P plus Q is 1. So this is a rank 1 tensor. Rank 1. And it's type 1, 0, which is just a contravariant vector. Okay, and when we say contravariant vector, we mean the components. Okay, the covariant one has P equals 0 and Q equals 1. So it's a rank 1 tensor, but it's of type 0, 1. So what we have here is how to get from the unbarred components to the barred components. So unbarred to barred. What about the inverse? Okay, we want to go from the barred components, and again there will be, let's say, P contravariant components and Q covariant components, beta 1 to beta Q. So how do we write the unbarred components? Let's call it I1 to IP and J1 up to JQ covariant components. So what does this equal? Okay, so how do we get from the barred to the unbarred? Well, there's an easy way of thinking about this, and it's realizing that we can call our coordinate system anything we want. So this top line takes us from the x coordinate system to the x bar, but we could have equally called this x bar and this x. Okay, they're just names for our coordinate system. So if we just relabel x to x bar and x bar to x in this equation, then we get the inverse. Hopefully that's clear. If it's not, have a little think. It's just the fact that we can call our coordinates anything we want, and this takes us from this side to this side. So if this side has the bar and this side has the doesn't have any bars, then we get the following. We get it's dx by dx, and the bar was on the top now, so we've relabeled x bar to x, so that just stays as x. There's an I1, and this is x, so we've relabeled that as x bar. Okay, so this is a Jacobian matrix element of J bar, and this is now a Jacobian matrix element of J. The inverse. Okay, and we just have the same. We keep going. Dx by dx bar. Let's have an alpha p and an IP. And for the covariant components, instead of this being the matrix element of J, we now have matrix elements of J bar, where we have dx, and x becomes x bar, and x bar becomes x. Times up to the nth one. Dx beta n with a bar on top, dx with no bar, jn. Okay, so that's the simple way of thinking what the inverse is. Okay, so let's now think about these components and why tensors are actually useful. But let's maybe first think about simple examples. So let's think about some examples, and let's have P, so the number of contravariant components, Q, the number of covariant components, what the rank is, R, and what we call it, so what the name is. Okay, so let's think about something, let's call it T. So what type of object is this? It has 0 contravariant components. It has 0 covariant components. The rank, which equals P plus Q, is 0. And this is called a scalar. So a scalar is a rank 0 tensor. Now let's think about something different. Let's call it a K. So this thing has 1 contravariant index and 0 covariant indices. So what's its rank? The rank R is P plus Q. So P plus Q is just 1. And this is called what? It's a rank 1 tensor. Okay, and you know what this is? It's called a vector, and it's a contravariant vector. And when we say contravariant vector, again, we mean contravariant components. Okay, but we just call it contravariant vector. Let's think about something called D, and maybe with indices alpha, beta, gamma. So P here, the number of contravariant indices is 1. The number of covariant indices is 2. So the rank of this thing is 3. Okay, and this is called, so we're getting general. So we have names for scalar and vectors because they're quite common. Anything above we just call a rank 3 tensor, and its type PQ 1, 2. Okay, so you would say that this is a type 1, 2 rank 3 tensor. Okay, so what we have here is very general. So let's think about a few examples of specific transformations. So let's think about a rank 1 contravariant tensor, I. So the transformation law for this is just given by, so a specific case of this with P equal to 1. So this is dx bar by dx alpha I, and we have a T I need alpha. Yep. Okay. So this is how a rank 1 this is a contravariant vector, sorry. This is how a contravariant vector transforms. Okay, so previous exam questions, when you sat the exams in an exam hall, would have asked you to write down the transformation law for a contravariant vector or a rank 2 tensor, rank 2 type 1, 1. Okay, so let's think about that. This is something, let's call it A, and it has 1 contravariant component, I, and 1 covariant component, J. So the transformation law for this, from the unbarred system to the barred system, involves 1 of these Jacobian matrix elements J bar for the contravariant index, dx bar I by dx alpha, and we have an A alpha beta Okay, so the alpha sums over the alpha. So this takes care of the contravariant index on this side. And you have the I, which gives you the superscript. And the covariant index transforms according to the J matrix. So this is dx by dx bar with beta on the top and a J on the bottom. Okay, so far we've only considered the components of a tensor. And when we looked at vectors, we looked at the components and also the basis vectors. Here we see that, or we find that we don't need to worry about the basis vectors, thankfully, because the basis vectors for this type of set of quantities is very complicated. And in the next part, we'll see why. So up to now, when we've talked about tensors, we've only talked about this set of components. The tensor itself involves, so let's call it T, and let's put a squiggly line underneath to denote the tensor. The tensor itself has components and basis vectors. And the basis vectors are as follows, and it's quite complicated. We have a basis vector for each one of these P contravariant components. So we have a natural basis vector for each one. So I1, I2, up to IP. And how do you put them together? Well, you put them together through what's called a vector cross product. And then you have a basis vector for all Q covariant components. And these are the dual basis vectors now. E, J1 crossed with E, J2, vector cross product, up to the last one, E, J, Q. Okay, so this thing is quite a complicated beast, and the good thing is we don't need to worry about it, and we never really need to worry about anything other than the components of a tensor. So we'll see what this cross product is in a bit more detail. But just like our vector, when we drew a vector A, and we said this thing is independent of any coordinate system, but if you choose a coordinate system, you can represent it in terms of components and basis vectors. Okay, and you could choose different components, the covariant ones with the different basis vectors. But this vector, this arrow in space, is independent of any coordinate system. This tensor is likewise. It's independent of any coordinate system. But if you choose a coordinate system, you choose a set of components. Well, you first choose a set of basis vectors, and then you have components that describe this tensor in that coordinate system. But the beauty is that we can add tensors, just like we can add vectors. A and B give you C. Oops. Okay. And if you're in the same coordinate system when you add A and B, let's think about this. A plus B equals the components of A, EI plus the components of B, EJ. Okay. And this is C. But if you pick one coordinate system to describe both of your vectors, then these basis vectors are the same. So you can write this as AI plus BI, EI equals C. Okay, so if you want to describe C when you know A and B, then all you have to do is add the components, AI and BI. So similarly, we can add tensors of the same type. So we can add. So for example, if we have a tensor R, I, J, K, L, M, and a different tensor, D, I, J, K, L, M. And when I say tensor, we're talking about the components of a tensor, but that's just what we say. Then you can make a tensor let's call it A, which also has the same number of indices, and it's just R, I, J, K, L, M plus D, I, J, K, L, M. And the reason you can do that is because the basis vectors are the same for both this and this, because you've chosen your coordinate system. So there's a tensor called R, and there's a tensor called D. And this R tensor is equal to these components times this basis vector. This set of basis vectors with P equals 2 and Q equals 3. So R and D have the same set of basis vectors. So you can factorize this out, and you're left with just a sum of the components R and D. And the beauty of tensors is that if you have an equation involving tensors, so here we have A equals R plus D. This is a tensor equation. Then you can always write this as A minus R minus D equals 0. Okay, and let's call the left-hand side big tensor T equals 0. So my pen's running out, so let's make this T equals 0. Okay. So you can always write a tensor equation in the form T equals 0. A tensor equation. Okay, the key word is equation. And if we go back and if we look at the components of T and how they transform, so we saw that the barred components for a tensor up to IP and J1 to JQ involved Jacobian matrix elements, T, alpha, So the point is, if your thing T equals 0 in one system, then it must equal 0 in the other coordinate system. Doesn't matter about all these guys. Okay, so this demonstrates that the tensors T, they represent geometrical and physical properties that are independent from the coordinate system. So in the course we'll be looking at tensor equations, and we're only going to be really concerned with the components of tensors. You'll be glad to know. Okay, so you don't need to worry about this hideous vector cross product of P plus Q basis vectors. Okay, so we'll focus on the tensor components, how they transform, and we'll think about equations involving the tensor components. Motivated by the fact that for tensor equations we can always take everything to one side and have the equation equal to 0. So if the equation is true in one coordinate system, it must be true in the other coordinate system. So it represents some fact of the universe that is independent of any coordinates.